Okay, let's start, everyone. Welcome to today's central exercise session. As usual, we will be available for your questions on chat. So please use chat.tum.de. Please use this channel here, MA9714-CE, to ask your questions. Today's chat moderator will be Tiago once again. Tiago, are you here?
Yes.
Great. Could you introduce yourself, please?
Yes. Hi, I'm Tiago. I'm a PhD student from the mathematics department. And yes, I will be the moderator today.
Okay, thanks a lot. So if you have any questions, post them to chat, and I'll either try to answer them here live on air, or Tiago will answer them on chat. As usual, I'd like to post a quick poll before we start. We'll be discussing sheet number 12 today. The main topics on sheet number 12 were parameterized curves, vector fields, an introduction to vector fields. And for the curves, we also talked about computing curve length and computing general line integrals. So I'd like to know what you found most challenging among these topics. Give you 10 more seconds to cast your vote. So far, vector fields has taken the lead. Okay, so I'll end the poll, and here's the results. So vector fields with 66% seem to be the most challenging topic, even though we didn't even really start talking about vector fields. Maybe things will become a little more clearer once we venture deeper into that field. And then it's line integrals and computing curve length. So we have one central exercise problem for each of these topics. So I'll try to discuss vector fields a little more, but again, we'll have more of that next week. Okay, let's have a look at our exercise sheet. So 12.8, that asks you to sketch two curves. That didn't seem to be that problematic, so I'll try and keep that short. So the first curve here is part A, gamma, with a parameter space from 0 to 6 pi, and it's going to be a curve in the plane, R2, defined as gamma of t equals sine t cosine of t. Now, there's one curve that you should know pretty well by now. That is the circle. And you know that the usual parametrization for the circle is this, cosine t, sine t. And usually, we just take t between 0 and 2 pi. So that is the circle with a radius 1. And this curve gamma here, that seems to be something similar. Two differences mainly. The first one is that parameter space. That's not 0 to 2 pi, but 0 to 6 pi. But that's not that much of a problem. All it says is we're not going through the circle just once, but we're going through the circle 3 times in a row, right? So first revolution is from 0 to 2 pi, then from 2 pi to 4 pi, and then from 4 pi to 6 pi. That's one more round. So we pass through that circle 3 times instead of just once. It doesn't change the sketch, it doesn't change the graph, but of course, if you evaluate an integral along that curve, it might change the value, right? Because basically you triple that integral. The other thing that has changed, that's probably a little more important, is the order here. So if you compare that, you will find that here we have the cosine and then the sine in the second coordinate. Here we have the sine and then the cosine. So what difference does that make? Let's have a quick look at the sketch. Okay, if you try and sketch that graph, this one here, then what you'll see is pretty much a circle again. So it doesn't seem to make a lot of difference. That's the graph of gamma. As I said, we're passing through that circle 3 times instead of just once. The other difference is the starting point. So if you look at the parameter t equals 0, what you get here is sine of 0, cosine of 0. That's the point 0, 1. In this parametrization, you will get 1, 0. So instead of starting here, the starting point for this circle is here at this point, right? So that's the difference. So here, this is the point t equals 0. And then what happens when you start at this point? Well, the sign, the first coordinate increases. If you go from 0 to positive values, that first coordinate will increase. The second coordinate starts at 1 and decreases. So that means if we're at this point here, then the first coordinate increases, we're going in this direction, and the second one decreases, we're going in this direction. So the direction along that curve is now this here, right? So we're turning this clockwise instead of counterclockwise. Let's visualize that with some arrows here. So that is the direction of that curve. Direction is clockwise. Whereas here, for that usual parametrization, the starting point would be 1, 0. And this parametrization would run counterclockwise. Okay, so those are the differences that you should take note of. It looks the same, it's still a circle, but the direction is different and the starting point is different. And if you evaluate an integral along that curve, those may make a lot of difference. So it's not just important how the curve looks, but also how it's parameterized sometimes. Okay, any questions so far, Tiago?
No, sorry.
No, okay. Good, so let's quickly talk about the second one. The second curve is given by the parameter space 0 to 1. Again, it's a curve in the plane in R2. And gamma of t is defined as t and t squared. Right, so that's an easy one. What we have here is one coordinate that just is t, that is the parameter. So basically we assign to every value of the parameter a value t squared. And that means what we get here is basically the graph of the function t maps to t squared. So if we want to draw this, we have a parameter space from 0 to 1. So let's say here's 1. Let's say here's 1 as well. Then what we get here is basically this function here. So that's the graph of the function t maps to t squared. Right? So if the first parameter of a curve is t, and you have a curve in the plane, then you could just interpret the second one, that second coordinate here, as a function of the parameter, and then the image is just the graph of that function. Okay, so vice versa, if you have a function and you want to write it as a curve, that's the way to do it. You just write t as the first parameter and function of t as the second one. Okay, any questions so far?
Still not.
Still not. Wonderful. So let's proceed to vector fields then. C12.9. So here we're just being asked to sketch a couple of vector fields, 2 vector fields to be precise. The first one is vector field V, defined on R2 without the 0. And then, of course, it has to map to R2, where V of x equals x over the norm of x. So for a vector field, what we do to visualize it, to sketch it, is we take a couple of points in the domain, in R2 here in that case, and to each of those points, we attach the value of V at that point as a little arrow. Yeah, so we basically see how the arrows change if we move along that plane. Now, what is special about this vector field is if you compute the norm of that V of x, then what you get is the norm of x over the norm of x. That norm of x is a scalar, so we can take that outside of the norm. And we're left with this here. And of course, this just cancels out. So the norm is always 1. All the vectors in that field have a norm of 1, so the length doesn't change. And what that means is you can draw that sketch pretty easily. So if that is our plane here, it's not defined at 0, but everywhere else it is defined. And everywhere else it just points in the direction of x itself, right? So this is the direction, and the length is always 1. The direction of a point is the connection of that point to the origin, or from the origin to that point, to be more precise. So what we get is basically like here, for example, the connection, the direction of that point is this one here. And we have to attach that vector to this point. So this is the vector field at that point. Same thing here. And here it's always pointing away from the origin, like that. And of course, we can also do this outside of the axis. And this is always the same length, always 1. Yeah, so same thing happens here and here and here. So this is the vector field here, okay? All vectors have the same length. They all point away from the origin in radial direction. So that's how this vector field here looks like. Questions about this one, Tiago?
Not about this, but someone asked if in the exam they are supposed to sketch circle or other geometric figures, and if they should make use of the automatic correction, the note-taking apps.
I would prefer you don't use automatic correction of your note-taking apps. If you're comfortable with those, then you can, of course, do that. But I would not demand that all circles be precisely round, right? I mean, that here is not exactly a round circle either. As long as it's clear that that is meant to be a circle, I'm good. Yeah, no need to have those precisely. So you can do that, but you don't have to do that. Other questions?
No, only this.
Good. So let's have a look at part B then. Might be quick today. Okay, part B, that's a little more complicated, but not that much actually. So we have a function, f of x1, x2, defined as x2 e to the x1 plus x2. And again, the question is for the vector field, that's defined as the gradient of f at the point x. The gradient defines a vector field because it assigns a vector to each point on the plane, each x1, x2 pair. So let's just compute that vector field to start with. So we need to compute that gradient. And if we differentiate that expression here with respect to x1, x1 only appears here. And that means basically that is the same expression once again. So we have x2, e to the x1 plus x2. That's the partial derivative with respect to x1. For x2, it's a little more interesting. That appears twice. So we need to use product rule here. So let's differentiate that, that first expression first. And then we're left with e to the x1 plus x2 plus x2 times. And if we differentiate that expression with respect to x2, that just reproduces. So we get that e to the x1 plus x2 again. Okay, so that's the gradient. And we can write that in a more convenient way by taking out this e to the x1 plus x2. And then we get x2 and 1 plus x2. Okay, so that looks extremely simple. Basically, if you want to sketch that vector field, first thing you should notice is this factor here only influences the length of the vectors. And it's exponential. That means if x1 and x2, or their sum, grows, then the vectors get bigger very fast. If those are negative numbers, then as they decrease, that vector tends to 0 very fast. So basically, for negative numbers, the vector field is going to almost vanish very soon. Of course, we also have the length of this vector here, but that's basically just linear. Oops, sorry, linear with x2. Yeah, so it doesn't really hold up to the exponential function here. Second thing you would notice is that this vector here depends only on x2, not on x1. So the direction of the vectors, and this part here determines the direction, this direction does not depend on x1, just on x2. So as we move along the x1 line, we don't change the value of x2, but just the value of x1. If you move in that direction parallel to the x1 axis, then the direction of the vectors remains the same, just their length that is changing. Okay, and that will hopefully help us to get to a quick sketch of the vector field here. So very roughly, and that's totally enough. Very roughly what we get is something like at 0, at the point 0, 0, we have e to the 0, that's 1, and then we have 0 and 1. So that means at 0, this is the right vector. And it also means as we move along this axis here, the direction doesn't change. The length will increase if we move in that direction, and it will decrease if we move in that direction. And it will do so pretty quickly. So qualitatively, something like this will happen. And it will decrease here, so we'll almost get zeros as we move to the left. Okay, and now what happens if we move away from that axis here? Let's move up first. Now what we can see there is, for example, if we move up here a little, let's say somewhere here, so we increase the x2 value, but we don't touch the x1 value, then of course this will increase. The vectors will get longer. And we get a vector of the form x2, 1 plus x2. So for example, if x2 is 1, then we'll have 1, 2. If x2 is 5, then we'll have 5, 6. Yeah, something like this. Okay, so what happens here is the vectors will bend a little. And they will get longer. So I should make this a little longer, actually. And again, as we now move along this axis, parallel to the x1 axis, it's just the length that will change, not the direction. And if you move up, the direction will also change a little. Yeah, so the vectors will start to bend a little more. And basically, that's what I want to see here. Now, if you move down, that's what we have to do. Explore this area a little. So let's say we have negative x2 values. Then, of course, this here will decrease. So we'll see very small vectors even sooner. And here, for example, if we have x2 equals -1, then we'll have -1, 0. So here at this point, we'll have -1, 0. Where are we? -1, 0. So that means we're moving in this direction here, right? And again, if we're moving along that line, the direction will not change, sorry, but of course the length will change. So this is getting longer in this direction and shorter if we move to the left, okay? And basically what happens above and below this line is the vectors will bend a little. If we're moving in this area here, the vectors will bend a little towards this direction more and more. So that change is continuous. That means if we're moving, like, for example, here, then we get something like this. And if we're moving down here, the vectors will bend downwards. So here we get something like this. Yeah, so basically that's the behavior of the vector field. As you can see, this is far from being precise. So it's mainly the qualitative behavior that I'm interested in when I ask you to sketch a vector field. If you want to see a little more precise solution here, let me just show you the plots. So this is the first one. It's not too bad. This here is the second one. Yeah, so you can see our qualitative thinking got us a good impression of how that vector field would behave, right? Here's the -1 line again. Oops. We drew that correctly. Here is the 0 line. We drew that one correctly. And you can see if we're moving here to the left, then the vectors will get very small quickly. And if we're moving to the right, they will increase quickly. For example, you can see that here, right? One more thing that you can see that I didn't talk about yet is if you take the function f and draw the contour lines of f. I drew some of those here. So that's a contour line, for example, or here's one other contour line here. Then the gradients always point in the direction of steepest ascent. That means they're pointing in the direction where the function value is increasing. And they are always pointing away perpendicularly from the contour lines, because along the contour lines, the value doesn't change at all. So the steepest ascent is always perpendicular to the contour lines. And you can see that nicely here, for example, right? So you have these vectors. Those are perpendicular to that contour line here. Okay, so if you have a contour plot already, and I'm asking you to please sketch the vector field that belongs to the gradient field of that function, then basically what you have to do is take the contour lines, determine the right direction. So determine whether it's this way or this way. You need to find out how the function increases. And then you need to get an idea of how the length of the vectors behaves. So the contour lines, level sets give you the direction. They don't give you the length right away. So you have to find out how that behaves. But otherwise, it would be a big help in drawing these vector field sketches. Okay, any questions about vector fields?
Yes, someone asked if you could explain again how to get the direction of the vectors.
How to get the direction of those vectors here? So by just looking at the expression. So this here, for example, this is just a real number. Let me write that. So that's just a real number that doesn't change the direction, just the length. But this is a vector. right? This in R2. So that will give you the direction of the vectors. And you'll notice it doesn't change with x1, it changes just with x2. So what I would then do is take a few selected x2 values and just compute the corresponding vectors. For example, x2 equals 0 is probably a good choice. So then we get e to the x1 times 0, 1. That means we're always pointing in 0, 1 direction, right? That's this way here, upwards, like that. For that line down here, I tried x2 equals -1. That will give me e to the x1 -1, and then -1, 0. So this time the x1 direction is -1, the x2 direction is 0. That means we get vectors pointing this way. And we can just do this for a few more selected values and then see how the vectors behave. And in this case, I'm lucky there's no x1. And that means if I'm moving these vectors, one of these vectors that I found, if I'm moving in this direction, then the direction of the vectors will not change. It's just the length that will change. Of course, that need not be the case in general. Yeah, then I would probably have to find how the change behaves here. So how the influence of x1 bends the vectors. So I'd always try and fix, if I can, the easier of the two, and then see how the vectors change if I increase or decrease the other of the two variables. So I hope that somehow answers the question. Any other questions?
No, some people are writing, but at the moment not.
So I guess let's proceed to 12:10 then. As
The
I said, we'll
person
have.
said thank you.
Okay, we'll have the opportunity to talk more about vector fields in the next week as well. Yeah. So this week's lecture videos will discuss vector fields and integrals over vector fields some more, and of course there'll be problems on that topic as well.
There is a question.
Hmm?
Someone asked, why did we take the norm of V in A?
Why did I take the norm of V? Basically, I wanted to know how long the vectors of that vector field are. And in this case, I mean, you can almost see that, right? So the vector field is the normalized version of the vector x. And normalized version, of course, means the vectors have length 1s, right? And that's what I verified here by taking the norm of those vectors. Turns out they all have length 1. And that's why all these arrows here are uniformly in length. They just change their direction. So I just wanted to prove that they really have length 1.
There is also one more question.
Yep.
Should we write down our observations concerning the behavior of the length of the vectors in the exam?
Should you write down? Well, that depends a little what I'm asking. If I'm just asking for a sketch, then that observation doesn't really matter. If I'm asking for a sketch and a justification, then of course you should let me know your reasonings for drawing the vector field just like this. So it depends on how I ask a question. Usually the statements will include whether I want justifications or just the result. Same as in Math 1. Okay, let's go on with 12:10 then. So in 12:10, we're computing the length of a curve. And the specific curve that we have is the so-called cycloid curve. So that's the curve defined on the interval from gamma to 2 pi onto the plane. And it's defined as t minus sine of t and 1 minus cosine t. Let me give you a quick idea of how that curve actually looks like. So that blue curve here, I can see here, that one, this is the cycloid curve that we're talking about. And the way it's constructed, imagine you have a wheel, like this circle here, and that circle rolls along the x1 axis, and you observe one point on the rim of that wheel, like this point here. Right? That started right here, and then as the wheel started rotating, that point moved upwards with the wheel rotation. And the curve here, the blue curve, that's exactly the curve that will be drawn by this point. If you attach a pen to that and then roll that circle on the plane, then this point would draw that curve here. Right? So that's half a rotation here, point is at the top, and then it starts to rotate down. And this gamma of t, that is the parametrization of that cycloid curve. Okay, but let's see how we compute the length of that curve. You do hopefully remember the formula for computing curve length. This one. So the length of a curve gamma that can be computed by integrating over the parameter space. So in this case, 0 to 2 pi. And the expression we integrate is the norm of gamma prime or gamma dot of t dt. So you integrate that norm, you get the length of a curve. And that's exactly what we're going to do. So the first thing we need is we need to compute gamma prime, and then the norm of that expression. So gamma prime, let's see, that means we have to take the derivative of that first coordinate and then the derivative of the second coordinate. So for the first we get 1 minus, and the derivative of the sine of t is the cosine of t. And for the second coordinate we get minus sine of t, so it's plus sine of t. Okay, so this is a derivative. And that means to compute that integral here, length of gamma is then this integral 0 to 2 pi of the norm of gamma prime of t dt. So what we get is the integral from 0 to 2 pi. And the norm is the square root of 1 minus cosine t squared plus sine t squared dt. Okay, so that means what we have is the square root of, let's say this is 1 minus 2 times the cosine of t plus cosine squared of t plus sine squared of t dt. So as cosine squared plus sine squared is 1, that means we are getting the integral of the square root of 2 minus 2 cosine of t. Okay, and to compute that integral, we can now use the trigonometric identity that is given in the problem statement. So of course that is there for a reason. And that identity is 1 minus the cosine of t equals 2 times sine squared of t over 2. Okay, so we'll use that. To use that, we have to take the square root of 2 out of the integral. And then we have exactly the expression square root of 1 minus cosine of t dt. So if we use that, then we get square root of 2 sine squared of t over 2. And again, let's take out the square root of 2. So we get 2 times this integral. And then the square root of the sine squared is, of course, sine t over 2. And to be precise, the square root should never be negative. So to be sure that this works as it should, we'll have to take the absolute value here. Now, a little word about the absolute value. As you can see, the parameter space is between 0 and 2 pi, and we look at the sine of t over 2. So that's the same thing as the sine between 0 and 2 pi over 2. So that's between 0 and pi. And you do hopefully remember the sine curve. Basically, that looks like this here. Right, so here's pi, here's 2 pi, here's 0. So we're evaluating sine of t over 2 between 0 and 2 pi, so that will be the same as sine of t between 0 and pi. That means the relevant part of that curve is this one. And that is non-negative. So that's why we can just do away with the absolute value here, because that value is positive or non-negative anyway, right? So this here is greater or equal to 0. All right, so let's do the integration. Last step. That is 2 times, and if we integrate the sine, the integral of the sine is minus the cosine of t over 2. If we differentiate that cosine of t over 2, what we get is minus the sine of t over 2 times 1 over 2. So to get the right result, we need to take this times 2, right? So minus 2 times the cosine of t over 2, that's the integral we're looking for. And of course, we have to evaluate that. So what we get is, let's see, minus 2 times the cosine of 2 pi over 2, that's the cosine of pi, minus minus, so plus 2 the cosine of 0. The cosine of pi is minus 1. So we have minus 2 times minus 1 is plus 2, and the cosine of 0 is 1. So that's 2 plus 2. So we get 2 times 4, and that is 8. So the length of that curve is 8. Okay, interesting enough, there's no pi in there or something, even if the curve looks kind of round. The length of that is simply 8. No complicated expressions. Okay, that's 1210. Any questions about this one?
Yes, someone asked if you could explain how the replacement of 1 minus cosine of t works.
How the replacement of 1 minus cosine of t, well, basically you just use the identity I gave you. If you have a look at the sheet, it says, let's scroll back a little, it says precisely, here we have it. It says this trigonometric identity could be helpful, and there it is, right? So I wouldn't expect you to know that. And if that was an exam question, I would also give you that identity, of course, right? So other way around, if you have a hint like that in the exam, in the statement, then it is probably useful somewhere. There might be other ways. So if you didn't use it, that does not necessarily mean you did something wrong. But of course, if the hint is in there, then you may just use that without questioning it, without proving it, without justifying it, right? That's why I put it here. Does that answer the question, or did you want to know how we could actually prove that identity?
Don't know. But second question is, someone asked if you could explain again what you did with the absolute value.
What is it with the absolute value? Okay, so we want to get rid of this absolute value basically. And usually the way, usually the way to do this would be to find out where this function is positive and where it's negative, so that we could then suitably treat that absolute value, right? In this case, this sine of t over 2, we're evaluating that between 0 and 2 pi, right? So we basically have a sine of a parameter that moves between 0 over 2 is 0, and 2 pi over 2, that would be pi. So that function is basically the same as the sine of t between 0 and pi. And here's the sine of t. Between 0 and pi, the curve looks like this green one here. So that means that function is non-negative everywhere on the whole domain of integration, right? And that means we can just do away with the absolute value. We don't need that. If the function would also be negative somewhere, then what we could do is we could just split up the integral, right? So we would split up into a positive part, a negative part, and possibly a positive part again, and so on, as necessary, so that you can split up the function into purely positive and purely negative parts. And in each of these parts, you could then do away with the absolute value by either just ignoring it or by putting a minus sign instead. Yeah, so that's the general way of dealing with absolute values in integrals. In this case, we're lucky the function is only non-negative on the whole domain. Does that answer the question?
Yes, thank you. And third question is, could you explain how you factored out the root of 2?
How I factored out the root of 2? Well, basically I did this twice. So first time here, this one. So what I did here is, what I did here is I took this integral and then I wrote this as root of 2 times 1 minus cosine t dt. And that's the same thing as square root of 2 times square root of 1 minus cosine t dt, right? And then I just took the 2 out. And well, the second time that happened was here. And again, that's the same thing as the integral from 0 to 2 pi, square root of 2 times square root of sine squared t over 2 dt. And then I just took this out. And square root of 2 times square root of 2 is equal to 2. I hope that answers this question as well.
Yes, thanks.
Any more questions?
No, this was the last.
Okay, great. So let's go on to 12, 11, sorry, the last one. C12, 11. So here we have a cylinder of radius 2 around the center 1, 2, the base in the x1, x2 plane, and the axis parallel to the x3 axis. And then it says the cylinder is cut off by the plane, more or less, given with the surface given through the function 2x1 plus 3x2. And we are asked to compute the lateral area of the remaining part of the cylinder below the graph. So let's try to make a quick sketch of that. So basically what we have here is something that looks, oops, that was a bit skewed. So I'll try that again, yeah. Something that looks like this here. So let's say we have x1, x2 here. Then we have the point 1, 2, that's roughly here. Right, so that is the center of our cylinder. And we have a cylinder of radius 2 in that plane. So we have a circle of radius 2 around here. Yeah, it's not quite 2. Let's make this a little larger, like this. The axis is parallel to x3, so that means the cylinder extends up here. Okay. I should probably draw it that high so that I can attach the function. So something like this. Okay, so that would be the cylinder. And now we have a surface given by that function f, defined on x1, x2. And we're saying that function cuts off the cylinder at some point. So instead of a plane cut like this one here, what we get is a surface, some hilly surface going through that cylinder, cutting it off. So in effect, we'll have something that looks rather like, I'm exaggerating, of course, something that looks like this here, right? So it's not sharp, clear cut, but instead it's something roundish, okay? That's how the cylinder looks, and we are asked to compute the lateral area. So that means the area below that curve here in the front, and of course also on the back, yeah? Okay, so what do we have to do here? Well, basically what we're doing is we're computing the area below a function graph. That's this function graph f here. The only complicating thing here is that function graph, we don't want to know that function graph along a line, straight line, like along the real line, for example, but we want to know the function graph along the circle. And that's exactly what line integrals were made for, basically. So we have a function that is derived from a higher dimensional function by regarding it just along a given line, in this case a circle, and then basically that's the same thing as a one-dimensional real valued function. Just the real line looks a little more complicated. It's not a line, it's a circle. But let's imagine you cut that circle, you roll that up, and then you have a one-dimensional function again. And we want to know the surface area, so the area below the graph. And that means basically what we need to do is compute a one-dimensional integral. What complicates it a little is that line here. So we have to integrate the function along the line to get our surface area. Okay, so that surface area that we are trying to compute, that is the integral of the function f along the circle that describes the base of the cylinder. So first thing we need to do is we need to parameterize that base. So let's circle around the base. You know the parameterization of a circle. So let's say we want something like gamma of t is the circle that's usually cosine t sine t. That would be a circle of radius 1. We want radius 2, so we need to add 2 times in front of that to just stretch the circle appropriately. And then the last thing we want is we need to move the center point of that circle. In this case, the center point would be the origin, and we want the center point to be the point 1, 2. So what we do is we just move all the points so that the origin is mapped to 1, 2. That means we just add the point 1, 2, right? So what you do is basically you take that circle here, blow it up. So blow up is something like this. And then you move it to be around this new point instead, yeah, but just by adding this vector 1, 2. That's what's happening here. So this is our curve, our base. And then we need to compute the integral. So, you know, the integral, line integral of f ds along the curve gamma. We have argued how that is defined in the lectures. And we need to integrate over the parameter space again. So here, parameter space, that is, again, t in 0 to 2 pi, because we're moving around that circle once, exactly once. So we integrate from 0 to 2 pi. And the line integral of the function f along that line is computed by just evaluating the function along the line. And then we need to somehow make up for the distortion that this line introduces. And that is precisely the same thing, basically the same thing as the length of the line locally. And you know the line length can be described by integrating over the norm of gamma prime of t. That's exactly what happens here as well. Okay, so this is the definition of the line integral of f along the curve gamma. And all that's left to do is we have to compute that value. So again, we will need gamma prime. If we compute gamma prime, then, well, first coordinate is 1 plus 2 times cosine of t. The 1 will vanish, of course. The derivative of the cosine is the negative sign. So we get minus 2 sine of t. And for the second coordinate, this one here, the 2 will vanish if we differentiate. And the derivative of the sine is the cosine. So we get 2 times cosine of t. Okay, so this is this derivative here. That means the norm of gamma prime of t is the square root of minus 2 sine t squared. So that's 4 sine squared t plus 2 cosine of t squared. So that's 4 cosine squared t. And that means we can take out the square root of 4, that's 2. And we are left with sine squared of t plus cosine squared of t. And that is exactly 1. So we have 2 times 1, that's 2. Okay, that makes things pretty convenient. So what we get here for this integral, we just use that formula. Basically, we have to evaluate f of gamma. F is the function f of x1, x2. Let me write that one down again. That was a function, where is it? Here, 2x1 plus 3x2. And x1, x2. We get those here. So x1 is 1 plus 2 times cosine t. x2 is 2 plus 2 times sine of t. So we evaluate this f. That means we have f of 1 plus 2 times, cosine of t. And 2 plus 2 times sine of t. That's f along the curve. And then we multiply with that norm of gamma prime. That's 2. Right? So this is the norm of gamma prime of t. And this is f at gamma t. And we want to integrate that with respect to t. So let's use that function definition. So that's 2 times x1 plus 3 times x2. So we get 2 times 1 plus 2 cosine of t plus 3 times 2 plus 2 sine of t times 2 dt. And that yields, so let's move the 2 outside. And then we get, let's see, that's 2 plus 4 cosine t plus 6 sine of t dt. So we have 2 times this integral over 2 plus 6 is 8. Well, the rest is just as it is, plus 4 cosine of t plus 6 sine of t dt. So we can integrate that one. That is 2. And then 8 is integrated to 8t. Then we get to the cosine of t. The integral of the cosine is the sine of t. So we have plus 4 times sine of t. And the integral of the sine is the negative cosine. So we have minus 6 cosine of t. Bounds from 0 to 2 pi. And now we just need to evaluate that. So for the upper bound, we get 8 times 2 pi, that's 16 pi, plus the sine at 2 pi, that is 0. The cosine at 2 pi is 1, so we get minus 6. And then minus the lower bound, that's minus 0. Minus, well, the sine at 0 is again 0. And the cosine at 0 is again 1, so that's plus 6. Okay, so we are left with, let's see, minus 6 plus 6, let's cancel out. So the only thing left is that 16 pi here, and of course the 2. So what we get is 32 pi. And that's the value that we were looking for. Okay, questions?
Yes, someone asked if you could explain again at the sketch the function which is responsible for the cutoff.
The function which is responsible for the cutoff. So basically, this is a very simple function in this case. Maybe let's try and sketch that one explicitly. So basically what you have here is something like you have this circle. I don't really mind how that circle looks like now. So here, that's the circle, that's the base of the cylinder. You have that cylinder above that circle. And then you're cutting it off by the surface generated by the function, so by the function graph, basically. In this case, the function is 2x1 plus 3x2. That's a plane. So it's not a plane that is parallel to the x1, x2 axis necessarily. It might be something like this, skewed, right? So what happens is you have this plane here. That's a little skewed in there. Something like this. That cuts this off. So you get something like that here. Yeah, the cylinder is cut. Something like this, that way. And so we're computing the lateral area below that cut here. Okay? And that's what happens. And of course, the same thing would be true if we did not have a plane, but instead something that has hills and valleys in it. That would, of course, then not leave a clear cut, but instead something bumpy. Yeah, but it doesn't really change anything apart from the computation, so it would become a little more complicated probably. Does that help? Does that answer the question?
Don't know, but
let's see what other questions we have.
Yeah. So could you explain what we are trying to compute regarding the integral? I'm having difficulties imagining it.
So with this line integral, what we are trying to compute is basically, again, you have this function that now lives along a line. So let's make another sketch here. Okay, so what we have is a curve down here in the x1, x2 plane. Curve like this. For example, a circle or some other curve, doesn't really matter. And then we have a function that's defined on x1, x2. So that's kind of hilly surface above this x1, x2, right? Something like, I don't know, maybe something like this. Yeah, imagine whatever you want here, like a saddle or something. And what we do basically is we just evaluate that function along that curve. So we take that curve and kind of project that onto the function surface. So this is the function along the curve. And what you could then do is you could regard that curve as something like an interval on the real line. Right? You would just cut the curve. Let's say here's t0. And we just cut the curve at this point. There's a starting point at the end point. And then we could take that curve, turn it into a line. Yeah? Imagine it's made of rubber or so. Yeah, you cut the rubber, you just stretch it to get a line. And what happens to this graph up here, when that is then also rolled up to get something that looks, let's say, roughly like this, maybe. Right? Depending on how complicated the function is, of course. Yeah, that's a simple case. So you have a function defined above an interval, on an interval, like this. And what we want to compute in this example is basically the area, this area here, on the front and also on the back, yeah, around the cylinder. That's the same area as this one here. Yeah, imagine you're making like a cylinder of paper, and then you have that complicated function that cuts the top. So you have your paper cylinder here, and for the top you make complicated cuts like this. Yeah, instead of a straight cut through, you make that more complicated. That's the function here. And you want to know the lateral area. So you cut your cylinder somewhere, like you make a cut here, you open it, and you just flatten that, right? And that's what happens basically in the line integral. We flatten that cylinder, and then we have a normal integral, normal real valued integral over a real interval. And this interval is more or less given by that curve, or by the parameter space of that curve, to be precise. Of course, we have to take the effect of that flattening into account. And that is precisely what that norm of gamma dot does. That kind of accounts for the change in area and volume that we encounter through the flattening process. Does that help?
I don't know, but yes, that helps. So there are a few more questions. Could you please again give a broad overview of the steps you did?
A broad overview of steps I did? Okay, yeah. So very high level. First step, I visualize the situation. I want to know what's going on. Second step, that's probably the one that needs the most creativity here, is coming up with a parametrization of that curve. So that's the curve that determines the base of the cylinder. That's the curve that we want to integrate along. And this is one possibility to do that. Of course, there's an infinite amount of possibilities to parameterize that curve. Whatever you do here is fine. It will all lead to the same results. And then, last thing I do is I'm taking this formula here to compute the line integral of f along that curve. That's the formula that we discussed in the lecture. And all I have to do here is I have to compute gamma prime. It's happening here. then the norm of gamma prime, that's happening here. So this is 2. And then I have to multiply this with f evaluated at gamma prime. That's happening here. F. So this is gamma. Sorry, not gamma prime. This is gamma. And this is f evaluated at gamma. And here's that 2 that comes from the norm. And then I just have to compute the integral like we did in the first semester already. That shouldn't be too complicated, hopefully. So that's the basic steps I need. Other questions?
Yes, someone asked if we could compute the volume here.
The volume of what? Of the cylinder?
I don't know. Okay, so the next one asks, I have difficulties with the order of integration when doing double or triple integral. Are there general rules or hints that might help me with this problem?
The order of integration. Okay, so in general, the order of integration, so for a function that is integrable, the order of integration would not matter. If the function is non-integrable, then of course that will make a difference or might make a difference. If you know it's integrable, then the order doesn't matter. That's Fabini's theorem, basically. Okay, so the only remaining problem here is you want to have some description of the domain that you're integrating over. And that's what's complicating things. Easiest case, we've talked about extensively, is your domain is a box, something like this. Yeah, so you have an interval here for the x1 part, and you have another interval here for the x2 part. And then it does not matter whether you integrate over x1 first and then x2. So that's the same thing as the other way around. Both intervals are not dependent on each other, so it does not change anything. In that case, you're free to choose whatever you want. Things get a little more complicated if you have what we call a normal domain. So in this case, you have an area that is not a box, that is more complicated than a box. For example, let's say something like this here, right? Half circle, half disk, better said, yeah? So in this case, here's an interval. So x1 is still an interval. Let's say that's 0, 1. But x2 might not be. x2 starts from 0, of course, and then extends all the way up to 1. But it doesn't fill the whole space. Something's missing. So actually, x2 depends on x1 in this case. So whatever value x1 has determines the upper bound for x2. Yeah, for example, if I'm here, then this is the upper bound. If I'm here, x1, then this is the upper bound. So x2 in this case is a function of x1. And that can be formulated as a normal domain. Normal domain means you have one variable that has just constant bounds. It's independent of all the others. And you have a second variable whose bounds depend on only that first variable. And if you have even higher dimensions, that chain might go on. You might have a third variable whose bounds then could depend on the first and on the second variable. So always on the preceding ones. Yeah, and for the fourth variable, the bounds might depend on variables 1, 2, and 3, and so on. So there's a clear chain of command, so to say. If that is the case, you have what is called a normal domain. And that means you can describe that as a series of inequalities. So here we have, sorry, for example, we have something like x1, x2 in R2. So where x1 is between 0 and 1, let's write this in orange. And then x2, that's a little more complicated. So the lower bound is always 0, this one here, it's constant. But the upper bound is a function of x1. And if this is a half disk, then this function here, you could easily derive that from the equation for the half disk. So the equation for that circle line is x1 squared plus x2 squared equals 1. And that means we can just solve this for x2. x2 is then 1 minus x1 squared, and then take the square root of that. And as x1 is between 0 and 1, that means this expression here is always non-negative, so we can take the square root safely. We don't have to make any case distinctions here. Okay, so that would be the upper bound in this example, something like this here. And of course, if you now integrate something over this domain, some function over this domain, then if you do this x2 integral, the bounds for this will depend on x1. So when you evaluate the x2 integral, you do the integration, you substitute the bounds, then you will have an expression that still depends on x1. So the x1 integration step needs to come after that. If you did that before, then you will be left with this x1 in the expression that you can't get rid of anymore. Okay? So with these normal domains, you need to integrate from right to left, right? So that the value, so the variable with the least dependencies comes on the outside, and the one with the most dependencies is on the inside. So in this case, the only possible order of resolution here is you need to integrate x1 on the outside and x2 on the inside. And here you would have something like from 0 to square root of 1 minus x1 squared. And for the x1 integral, you would just have constants, 0 to 1 in this example here. Yeah, so the expression, after you evaluate that green integral, you get an expression that still depends on this here. And then you integrate with respect to x1, and you evaluate that, and you just have constants then. So in this case, the order of integration matters. And of course, just as a side note, probably the easier way to integrate over domains like this would be to use polar coordinates. But of course, you could also do it like that. Okay, does that help? Does that answer the question about order of integration?
There is one more question. Oh,
no problem. By the way, just one thing I'd like to add here. Of course, that description for the normal domain might also not be uniquely determined. Yeah, so that's something that I came up with right now. There might be other ways to describe that very same normal domain. In that way, in this case, this is probably the most convenient one, but sometimes it's not that easy to see which is most convenient and which is not. And there's usually more than one way to describe the same normal domain, and that description will then determine the order of integration. It's not the geometry itself, it's the description that you choose. That determines the order of integration. So depending on your description, your order might be different than mine. Okay, any more questions, Tiago?
Yes, someone asked, how did you come up with the function for gamma?
The function for gamma, where was my function for gamma? This one here, I guess. Yeah, well, so this one, that's the parametrization of the circle. You know that one, cosine, sine. I want in a circle of radius 2. Radius 2 means this is radius 1, so I just need to multiply everything by 2. So radius 1 here. I just blow up the result by multiplying that by 2. I have a radius 2 circle around the origin. And then I need to translate that circle so that it does not, it's not a circle around the origin anymore, but around the point 1, 2. So let's say 1, 2 is here. And I want this circle. So I'm taking that circle and I'm translating it by adding this vector here. So, and then that means every point is moved, like this one is moved here, this one is moved here, the origin is moved here, this point is moving here, and so on. Right? That's what happens here. I just add 1, 2. That's how I came up with that parametrization.
Last question here about the volume thing again. So he asked, could we also compute the volume here? And now same person asks, I mean the volume of the cylinder under the plane. This would work just as we already did with the transformations, right?
Yes, yeah, sure. So the volume, we could, if we take this cylinder here, and instead of the surface area, we are interested in the volume, like the volume below that green curve here. Then we would not do the line integral, but instead we would do the volume integral, right? So the volume of that cylinder, again below the green curve, we just compute the volume integral over, let's say, well, what do we call this area? Let's call it C. I hope C is not reserved anywhere. And we just need to compute that function f of x1, x2, dx1, x2 over the cylinder C. Where C is the base of the cylinder, sorry. So that's the base of cylinder. And then, of course, we need to come up with a description of that base. And again, the easiest way to do this is probably using polar coordinates. And then using the change of variables formula to compute that integral. Give that a try, actually. That seems like a nice exercise problem. We did similar things, so it shouldn't be too hard to come up with that yourself.
Yeah, one last question here. So how do we know when we use cosine t sine t definition of a circle and when x1 squared plus x2 squared 1/2, everything
Okay.
1/2?
Yeah, so we have these two descriptions of a circle. The one is as a curve. So the description as a curve is this one here, t insert to 2 pi for the whole circle. And then we also have the description all x1, x2 with x1 squared plus x2 squared equals 1 squared, radius squared in general. Okay, so those are two possible descriptions of a curve, of a circle, sorry. That one is explicit, meaning that you just substitute one possible parameter, t, and you get a point on the circle. And this one is implicit, meaning you can't really compute directly points on the circle. You could just check. So if I give you a point, you could easily check whether it's on the circle or not. It's not so easy here, because you'd have to solve for the right t to see that. So basically, both are possibilities to describe a circle, one explicit, one implicit. The question is, what is necessary for the given task at hand? What is more helpful? In some cases, this description is more helpful. In other cases, this is more helpful. So I can't really give a general answer to that one. It really depends on the problem statement. You should keep both in mind and then see what you actually need. If you need an explicit description as a curve, this is the one to go. If you need an implicit description, this is the right one. Sometimes you need a functional dependence of x1 and x2, then probably you would use this one and then solve for x1 or x2. And of course, you might have to need a few case distinctions here, right? Because you need to do square roots. And of course, that is only possible if the argument of the square root is non-negative. So you might have to use case distinctions to do this. But again, it depends on the statement, on the problem that you're trying to solve. Anything else, Tiago?
No, this was the last.
Okay, wonderful. And that was the last question. And this concludes our central exercise session for today. On Thursday, we'll have tutorials again. So you're welcome to join us there if you have any more questions. Of course, you're also welcome to ask questions that do not refer to the current exercise sheet. Next Monday, there'll be another central exercise session on sheet 13. There will not be a sheet 14. So sheet 13 is the last one. It's a little longer, so it basically counts for 2 sheets. And we'll discuss this next Monday in the central exercise session. And in case you have not noticed yet, there will be no more videos next week. So this is the last week of lecture videos as well. So you should be able to ask all of your questions during the last week of the semester. So I'll see you on Thursday, hopefully, or on Monday. Bye.